Welcome to this live stream. Today we're going to take our line buffers and put it into a window that shifts one direction every clock cycle of all the outputs it reads. So this idea. So we're going to have so many. We have n number of line buffers. We're going to write to one and read from others. Incoming data that's being written is placed in bottom right of window. The other four filters. For line buffers, the other n-1 line buffer read values are placed on the right side of, I think it's gonna be really matter which side the window is, doesn't. I think we want to do this on the left, bottom left of the window. Yeah. On the left side of the window. Left. Yeah. So we need to figure out how we're gonna do the indices. So we're going to need a line of indices. We have sub y count. So yeah, we're going to use a sub y count. And the one that's going to be written is 0 sub y count. But we could just do a vector differently than that, right? Now we can just do 0. So let's take this process right here. Put this up here. We're not using the right vectors. Let's forget about that. Have the x count, but we need to put in a if yeah, just do like a reset right now. So if then else. Here we might as well just say x count equals others. Now we need a 4, so we're gonna do a 4 for I in range 0 to look at what I did on so 4 in range loop and loop, okay, loop and loop. And so what we're going to take is we're going to take the sub y count, right? And say of I of big I equal to sign No. Okay, so and then one, and if subcount is equal to what? Kernel size minus 1, and this is really minus 2 because of the way you want to catch it before it goes to the minus. I think, yeah, we have to go with that number. Okay, so we're good. Now we want to say if basically if subcount 0 is 0. Okay, now so let's get the bottom of the window. So we're gonna say the bottom of the window is window let's open up our type package to see what T window is. T window turn to array size. So yeah. You want kernel size times kernel size 1. Array. I want kernel size minus 1. Minus 1. We'll make this a on that side, 2 on that side. Oh. So this is generically for the 5x5, right? And then we want to do line out. Yeah, I gotta think about this. Where are we coming from? Do we want to do the index on the window or the index on the line out? 1 should be right above it. So you're saying we should do subcount. That's not how it should. How it should. Yes, it should be. We want to do, and because the lines are going to change. What line does this one represent? Of subcount 0. That's what we want to do. So whatever that one's, that's the one we're writing to, and then 1 is the one that was just written to. Okay. My brain's working. So whatever subcount 0 is, that's the one we're writing to. And that's true. And subcount 1 is one we just written to, and subcount 2 and subcount 3 are the ones, the previous ones we've written to. Now, we want to make this a by n one. Window. Okay. Good way to simulate this. We're going to want to reset it. We're going to want to set grade to some value and run. I want to get the X count to go that high. Okay, yeah, let's go for a relation behavioral thing. The only thing I can think of adding is the other shifting. We might be able to do a quick for loop about that. Oh, I forgot the type of type package to make sure it was 5. I have to regenerate if it's not 5. Okay, let's see, type package, run 5, that's good. So we're going to restart it. Let's, okay, as we can see here, this is the wrong simulation. To go here, we have to go to hierarchy and go to simulation, see what the top file that is specified for simulation is. Hierarchy, simulation sources, line buffer, set as top for simulation. Updating. And we hit run simulation, run behavior simulation. So Want to do clock, do reset high, set gray as 1, run for a bit, set clock, reset low, and then keep running it and see what gets updated and what doesn't get updated. Let this start. So we're gonna force a clock, 10 leading to 1, leading to 0. Good. Reset. We're gonna force a constant, 1. Gray. We're gonna force a constant, 1. I don't really care about valid. Let's run it for 20 nanoseconds. Ray sizes do not match. Ray has 3. Ray has. Oh, my bad. I feel like so. Let's see. We want first restart. Then we're gonna add a clock again. Let's go add that gray and then run that for 20 seconds. And see. Okay, it looks good. Now we're gonna set the reset low. So like low right now. Run 100 nanoseconds. Our X count is increasing. Let's check our window reg. That's good. I don't know why these are 0. I'm not assigning them to anything. Oh, we have those are the U's they're coming from. Okay. And Lineout. Valid. That's gonna be a hard thing to run. So let's run it for 1 millisecond. So our subwide count. That's changing rather frequent. So I mean that's almost okay. Anyway, we can do like an incrementing value. But then if we do window reg, Okay. So it looks like it's working. What we want to do is then restart this. Run it. Clock at the reset. Then we want to run it. Clock. Gray. And we want nanosecond. Set to 0. We want to run it for 1920 nanoseconds. We want to set gray to 2 seconds. Nanosecond. 4, 5. Oh, that many. 7. 8. 9. A. B. Let's see what we got here. Um, 6, 7, 8, 9. 1, 2, 3, 4, 6. Okay, and then we're gonna check the window. So like 6, 7, 8, pressing up. Nine. So you think we did it wrong? So we start at 0. Is 1. So we need to flip the. So this should be kernel size minus that. I'm getting. So I'm gonna do another for loop. Size. Do a 1 size. Kernel size minus kernel size. So, I mean, put I there right quick. What I right there. We don't agree with that, right? Because kernel size -1 minus. Oh, but it's going to be kernel size -1 minus that, so it should work out. Oop. Okay, so okay, let's I made that window. Copy over our code here that we're so first we're gonna restart. And we're gonna force clock 1, 0, 10 nanoseconds. Start. And we're gonna force constant 1. Force here 1. Okay. And we're gonna run 20 nanoseconds. This to 0. We're gonna run 1920. 1920 10 nanoseconds. And we're gonna set this to 2. 3, 4, 5, 6, 7, 8, 9, A. Go ahead and do B, C, D, E, F, B. I was doing this something different. I guess I could get VS Code or something. That. So okay, so we have 1, 2, and 1, and 3, 2, 1. Okay. Next thing is our for loop. This is gonna be a nested for loop, so we can get everything going good. So we're gonna want. Oh, I guess we could just do it. We're gonna want 0 here, and we're gonna end a loop. We're gonna want for j in j in 1 to kernel size -1 loop and loop. So what we want to do is we want to say j -1. So we want to say window reg of I times j can only go to 16 max, and we need one of them to stay solid. I'm trying to think of a fun way to do this. That's where oh. That gives the 0, right? Close. There's still kernel size 5. Well, 5's the next row. Oh, this is confusing. Oh, is this confusing? Hmm. So let's figure it out. So here we basically want simple transaction from 1 to 0 as an example. We want 24 to 23. Stop on timer. We do not want 5 to 4. So let's go 5 to 4. Well, we do have 1 times kernel size, so it'll be 5 on the right, and then 1 times kernel size minus 1 would be that one on the left. Do we want a plus 1? Do we want to say 0 to kernel size? Zero will just destroy everything on the bottom. The minus 1. You want another minus 1? So let's think about this. Kernel size times kernel size minus 1 is not going to reach our top phase. Right? We need a plus 1 somewhere. Or do we do this? What happens here, let's see. Kernel size times kernel size 25, 24 goes to 23. Okay, well, what's the first end of the first row? First one's gonna be we do not want 20 to 19, right? Okay, how would 20 to 19 happen? 20 to 19 would happen when one is 5 and one is 4. I'm not liking this. Bothering. I think I know why it's bothering me. Normally when you do indexing like this, you would then add something to it that like this would be times 5 times the kernel size, not 1 2 kernel size times 1 2 the kernel size. So what you're saying is we want to go from 0 to 4. So yeah, let's do this index wise. We want to go 0, kernel size minus 1 times kernel size. So we're going to put the kernel size plus j, right? And then we want to go from 1 to kernel size minus 1. That gives the 4. Minus 1. Because it's 5 times 4, 20 minus. So what happens here is we have 0 to 4 times 5. The top one would be 20. 20 plus 5 be 24 minus 1. Okay, cool. Brain hurts. I don't want that one. Don't want. For 5, 8 plus 1 would be 6. Yeah. Relaunch. See if the values carry over delicately. I'm watching that one. Okay. Okay. There we go. That's what we want to see. Boom, boom, boom. Carry it over. Let's go down to the fun stuff. Something. But the next clock cycle. I must have been. MCB A 8. So here's where the values change our clock cycle after that. For some reason, 6 per cycle. And it's just that it ran a cycle or less. It's carried on. See, when did these things line up exactly? They do. Oh, but these things are changing a cycle at a cycle after. You need to change exactly with the need to be they need to be read on the cycle before, we're saying. These are if lineout is concurrent and not registered. Register we want cycle earlier. That way numbers would change and it would change. So we're talking about have, and then we just say teen, right? And we end if there. We want to do the whole the whole subcount here. What happens? We want it to be read. We want these register values, updated values. We want this to line up a clock cycle earlier. So, and we can just recompile that real quick. Okay, so we have our window. So the next two things we have to do is we have to propagate the valids all the way through, so valid data is propagated correctly. Add a FIFO. Necessary to add a FIFO now. And then we have to add put an IP core and have the AXI register control everything. So we'll look at getting the valids going next turn. That shouldn't take too long. It'll be fun counting how these things register out. Yep. Ooh. So we go here. We want to see those now line up perfectly with So we did something we did not want to. Because like the see, go to where it's fully buffered. Okay, here we should. I don't agree. And okay, so we didn't do that like a radix that too. And so they're changing to new value. Oh, but we're saying it shouldn't be read until this cycle. So you're saying we're updating this? Read and with that where the new value should happen. So that should be B and that should be A. Okay. Let's go back to what we had before. Okay, let's run that. So the oh, let's go to B. Hanging out. So that's correct. So five, B, 5, 9. All good except for this one right here. So what we're saying was 4 is 4 in this. So 4 is gonna be -1. So yeah. Do the one right after there. And read the 0 from that element 9. Just reading. So something's being registered. Not registering something. So because new input goes there, let's save to 0. So reading the 0 value, putting it there. We didn't need, you're saying we need to delay the gray one? Writing. But here we're reading from 0. I'm going to assign it to there. We want to immediately act upon. So you're saying that concurrent not registered. But I mean, it is being registered in a way right there. So we could register the outputs again, right? We're saving it, adding it to this one. So this one would still be gray. When do these guys change? And so the shifting is just that the register of the shifting is happening. So I mean, my solution would be to copy that and stick that there, right? That would be my solution, because what's happening is our indexes are changing and that's being registered, and then we read from the line buffers and that's being registered. So if we read, if there was no registering there, I mean, it technically is registered in a location. My question is, to line up there. We all save and all read the same registry. And we could register the writes. Okay, let's run synthesis real quick to see how it does. How could we do that? I assume we would have to register. Want to. Okay, let's see how. Oh, so this. Oh, so it worked. Let's see what we got. Synthesis was rather quick. So, report utilization. Summary. We lost our BRAMs. There's a distributed RAM. I don't like that. Maybe we will have to play around with this inside so it comes out. Okay, so let's save this. Even though the functionality is not perfect, let's go ahead and run synthesis on. I want to see what the results are, and that'll probably be it for the stream. I'll have to think about the correct placement. I mean, we just gotta register the indexes, I think, or when we want to write them and register the gray value. We're using 12% of flat RAM. Seems kind of significant. Let's see how many block RAMs we do. So right now we have a little issue where the timing doesn't match up perfectly, but I'll go figure it out. I just want the utilization. Right, yeah, it's much better. I want like 5% VRAMs. Okay, so that's what we're gonna try. I will go play with it, get that to work. But yeah, thanks for watching. I will see you on Friday. Bye.